the major topics, and you tell me what if you need anything for test from chapter 3. Okay. Differentiation, graphing a piecewise defined function, differentiating a quotient, differentiating a product, reading from a graph that we did together in class. Everything was done in class. Differentiating quotients, limits that you can, if you'd like to apply L'Hopital's rule, since we discussed L'Hopital's rule from chapter 3, I'm fine with that, of course. The derivative of radical functions, chain rule, reading from a table like you read from a graph, the same thing. Differentiating the inverse trig functions, implicit differentiation, differentiating a function raised to a function, finding velocity, acceleration, cost, marginal cost, linear approximation, approximating using differentials, differentiating hyperbolic sine cosine hyperbolic tangent, and another implicit differentiation. That's the entire test, 23 questions. Any topic that you would like to discuss before we go back to chapter 4? Any problem that you would like to work on from chapter 3, from chapter 4, anything?
I have a particular question in mind, but
yes.
I was wondering if we could work on something with hyperbolic function.
Yes, of course. So that's section 3.10. In section 3.10, I'm looking at basically at the end of the chapter. So let's say something with hyperbolic function, let's say like 45, natural log of hyperbolic cosine 3x. 45 on 265. I'm glad the taxes are not due today because I haven't even started. Okay, 45 on 265. So a y equals natural log of hyperbolic cosine 3x. So we want to differentiate this function. I'm just signing myself out of WebAssign. Done. So we want to differentiate this function. Obviously we have 3 functions. This will be the first, this will be the second, and this will be the innermost. So when I differentiate log, I get 1 over hyperbolic cosine 3x. Then I have to multiply by hyperbolic cosine prime, which is hyperbolic sine, multiply by the inner function prime, which is 3. It happens that this ratio is hyperbolic tangent. And that's it.
For the purpose of derivatives, how does the fact that it's a hyperbolic change manipulating the function?
Oh, well, I'm not manipulating here at all. This is not a limit, and I'm not changing. I'm just finding the derivative. So I have, say it again?
Or rather, when you're just finding derivatives, the fact that cosine is hyperbolic versus non-hyperbolic.
Oh, yeah, the derivatives. So the hyperbolic cosine is not negative. Hyperbolic cosine prime is not negative hyperbolic sine.
Right, okay.
So remember, these look like trig functions. They are not. So remember, hyperbolic sine x is e to the x minus e to negative x over 2. So hyperbolic sine is a combination of exponential functions. And so is hyperbolic cosine. The fact they call them, they put a sine and cosine, tangent, cotangent in front of hyperbolic, is because they have some properties. It happens that they have some properties similar to the properties of trig functions, but they are not trig functions. They are combos of exponential functions. Is that better?
Yeah, would it be expected to, like, instead of having like some function, but like sine, instead writing ex minus b?
Yeah, you will not have to do that unless you have to evaluate it.
Okay.
Because I don't think, where's my calculator? I don't know if the calculator has these functions anywhere. If you find them, let me know. Numbers, complex, no, I don't think we have these functions. So if you want to evaluate a hyperbolic sine of 5, you will have to put it in. 5, negative 5 here, and over 2. I don't think we have any a way of, I don't know. I don't know if we have anything. I have never looked because I always knew the formula, so what they equal to. But it's a very good question. If you find those in the catalog, maybe. Yeah, let me look at see. Yeah, it doesn't jump. I was hoping it would jump. I know there is a way to jump to see. I'm just curious now. Thank you for asking. Yes, it's here. Look at that. So it is on the catalog, second in catalog. And you'll find hyperbolic cosine, and you will also find hyperbolic cosine inverse. So the inverse of that function. So they are in catalog. And hyperbolic sine should be there too. Okay, I remember how to do the jump. Here it is, hyperbolic sine. And even hyperbolic sine inverse. Okay? So you do have it in this one. And I think the other ones have it too, then, if this one has it. I never used it. That's why I wasn't sure, but thank you for asking. Good. Anything else that you would like to go back to? Anything else?
Somebody in the other class had mentioned doing sort of like a run through, but not necessarily like a full evaluation of the example test you've given us, but trying to picking through this. Is that acceptable or no?
Yeah, that's what I did. I gave you the topics and was waiting for you to choose. If you have something to choose, I'll do it. If you don't have anything, then I'll move on.
That's right. Okay.
But I will be more than happy. You know, you can ask later or right now if you have anything. Anyone can ask. That's why I went through the topics. Anyone?
Okay, nothing. Thank you, then.
Okay, anything. Anyone else? But I will continue, and if you find something, I will always stop. Now, if you have questions between now and Sunday, I will definitely answer your questions. So I have an online calculus class, and I'm just looking to see if he answered. So he had a question. This is their first test, and here was the answer. I put the answer for him, and I also wrote some notes. But I haven't heard back, and I said if you need a Zoom session, so I haven't heard back from him. So this was one student I've never met because he's in my online class. So of course that's an option as well. Anything else? Anything? Okay, well, let me know. So right now I wanted to see if you need more examples of graphing. If you say no, then we'll continue with optimization, and then we'll do more examples when we start reviewing for test 3. Or we can choose any problem you'd like. Page 317, anything from here. We had pretty much all types, rational, radical, even trig functions we had, polynomial. But if you feel like working on another problem right now, we can choose another problem right now. If not, I will, 4.6, you can read, we're using graphing calculators all the time. But I would like to start optimization problems. But let me know if you want another graphing situation. Or we wait till we start reviewing. Let me know. Can anyone say anything so I know what to do?
Yeah, I mean, I think we can maybe move forward, and if we come to questions that we might have for the review.
Okay, so we'll select other problems for the review. So now another application, remember thank you, Derek. Remember in this chapter, in chapter 4, we are mainly looking at 3 different applications. One we just finished, graphing. The second one is optimization. Like with related rates, I can spend a month on this one. There are so many different situations. And the last one, which is the easiest of everything, in my opinion, is Newton's method. One of my students last semester sent me an email from NSA saying, well, I'm working with Newton's method right now, and I was thinking about you. So I thought that was cute. Okay, so optimization, section 4.7. Optimization is a big, big branch of math, like algebra, like calculus, like trig, like geometry. Optimization is huge. It deals with max, min of functions. That's what it deals with. Max, min of functions. Well, of course, I have to have the function in order to find its max, min. How will I find its max, min? Of course, determining the derivative. The first derivative, of course. Okay, so let's start with a simple example. On page 332. Okay, so let's take a look at a box with a square base. 14, page 332, I'm going to write it down in a minute. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Okay, so let's take notes on the problem. 14 on page 332. We have a box with a square base. X, 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 of course, at the top, and some height. Square base and open top, no lid at the top. It has to have a volume, they say, of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. I have to put this away because it's so heavy. Okay. Minimize the amount of material used. Which means that I have to have a function that represents the amount of material used that I have to find the minimum for. So when we talk about the material used to create a box, what am I thinking of? I have material to create a box. So what am I thinking about? I'm thinking about length, I'm thinking about area, I'm thinking about volume. What am I thinking about when I create a box with an open top? So here I have some material and I want to create a box. And here's my box. It would not have a square base, but it's going to be a box. Here it is. It's leaking, but you understand what I mean. So here's the box. I know it's not, just bear with me and say it's a box. Okay, so then what does that mean? I'm interested in, anyone can say anything?
Just the minimum surface area.
Surface area. Very good. So for this situation, the surface area would be, it's an open box, open top, so it will have the base and 4 identical sides. Why 4 identical? Only because the base is a square. So x times h, x times h, x times h in all situations. So the surface area, S, will be the area of a square, which is x squared, plus 4 areas of the sides. They are equal. So x times h. Okay. We don't know how to differentiate functions of 2 variables. So somehow one of these variables have to go away. One of the variables has to go away. So I'm hoping that I can remove h somehow. I do have a piece of information that I have not used before or yet. And I know that the volume of this box is 32,000 square feet, cubic centimeters, of course. But what is the formula for the volume of this?
Area times height.
Area of the base times height. Very good. So it's the area of the base multiplied by the height. So what I have so far is this. From here, I have that x squared times h equals 32,000. I can solve for h. So then h equals 32,000 divided by x squared. And I can plug this in here. And now I can say with confidence that s is indeed a function of x only. X squared plus 4x multiplied by the height, which is 32,000 divided by x squared. I simplify, and I get fully simplified this function. So 128,000 divided by x. And this is a major accomplishment because I'm asked to find the minimum of a function that I have now. I have the area or the amount of the material used. I have it. It's right here. It's this. Now I'm asked to minimize it. How do I proceed? So I'm asked to find basically I'm asked to find x and h for a minimum surface area. So how do I proceed?
Differentiate.
Yes, very good. I have to find critical numbers first. So when I differentiate x squared, I get 2x. Very useful to remember. What is the derivative of 1 over x?
Negative, 128,000 over negative x squared.
Excellent. Now, in order to find critical numbers, I have to change this into a product or a ratio. So I would have to find the least common denominator, multiply this by x squared, 2x cubed minus 128,000. And now critical numbers, if you remember, they come from two sources, from s prime being 0 or from s prime being undefined. But there is no possibility here because the function is not defined at 0 and so is its derivative. So no critical numbers coming from s prime being 0. So then, from s prime being undefined. So now we analyze s prime being 0. So 2x cubed minus 128,000 equals 0 because a fraction is 0 only when the numerator is 0. I will definitely divide by 2 and move this to the other side and get 64,000. Yes, I have to take the cube root, and there is only one real number as the answer. So the cube root of 64 is 4, the cube root of 1,000 is 10. And this is centimeters. So if the base of the box is 40 centimeters, obviously the height will be 32,000 divided by 40 squared. And this is 20. And I can go my merry way. No, not enough. And this is crucial right now, extremely important. Please understand that there is no guarantee that this gives a minimum. I haven't proved anything. I only said that the critical number for the function is 40. If x is 40, then age is 20. But I have not proved, I have not convinced you that 40 gives a minimum. And I'm trying to do this right now. So I'm looking at the function, which is this. I have to study the sign on this side and study the sign on this side. And then I will convince you that it gives a minimum. So if I plug in 0, I'm not going to discuss the denominator. The denominator makes, it's always positive. So I'm looking at the numerator. If I plug in 0, this is negative. If I plug in 1,000, 2 times 1,000 cubed minus this will definitely be positive. Now I did convince you that this is indeed a minimum. So S of 40, not S prime, but S of 40 is definitely minimum surface area. Minimum amount of material used to create the box.